Good afternoon, everyone. Sorry for being late. As Professor just mentioned, this paper was cited by the Nobel Prize. It was very surprising. And this paper is a tutorial paper published in Nature Reviews. And it was super fascinating for me to read, and I learned a lot. But at the same time, it's also very challenging. So I will try my best to explain what I've learned and what Ising Machine is. So the title is Ising Machines are hardware solvers of combinatorial optimization problems. In computer science, we have a lot of NPR problems, and they are really valuable, but they are really hard, meaning that they require exponential amount of time in terms of complexity classes to solve. But they are also once and for all, meaning that if you solve one of them, you can map the solution to that problem into other solving other problems. When I was reading this paper, I was really looking for a polynomial time solution to those problems. But in fact, this paper answers the question, what are the non-digital approaches to the problem solving. And the key insight is that we can map most of the problems into something called an Ising Hamiltonian. So it's a computational model that we can map those problems into in polynomial time. So this is the mathematical formulation of Ising Hamiltonian. And to break this formulation down, first we have a vector of spins, the deltas. And the spins takes two values, they are binary, and I'd like to think of them as magnets, right? So in this case, we have three magnets, and when we have magnets, they are polarized, meaning that they have a north base and a south base. When we put them together, we have the interaction between them, right? So in this case, the first two are attracting each other, the second, but if we try to approach the third one to the second one, they will repel each other, creating a very high energy magnetic field. And we call this the first interaction, the in phase, and the second interaction out of phase. By the way, please feel free to interrupt me whenever there's anything unclear.
The first two don't match, and the last two don't match.
That is true, sorry, yeah. Let me see if I can kill the evidence. Yes, yeah, exactly. I just killed the evidence. So the second and the third are now out of phase because they are repelling each other, and the energy between them are higher compared to the energy between the first two. And we can further add on to that by creating, we can control the amount of interaction between them by inserting something called coupling, right, or connectivity. And this is represented by the J matrix. And further adding on to that, we can also have bias terms, which are, you can think of them external energies that we apply to every single spin. So if they are strong enough, they can flip some of them or all of them in terms of their configuration, spin configuration. And as we will see from the second paper we'll discuss in a minute, so Ising Hamiltonian can be simplified in this form by fusing kind of the second bias term into the first term. So in this case, to put things into perspective, we have a ring, a bunch of spins arranged in a ring, and in this case, they are all pointing upwards, meaning that they have the same direction. If we put numbers on it, and then we can, specify the configuration, the connectivity among them using the J matrix. Yeah, please.
Are you going to say what are the problem variables?
Yes, I will. I will find out. But yeah, so a professor asked what the solution variables are and what the solutions are. Yeah. So the configurations are representing by the delta vector, and those are the kind of the variables that we have, and the final. What we are varying is the J matrix, the connectivity, and the energy will apply to it. External energy, and the whole Ising Hamiltonian represents the total energy of the system, H. And we'll be looking at how we map this onto a real-world problem. And yes, so then we can see that, for example, 1 is connected to 2, 5, and 8. And in this case, we have a very high energy state because they are all of them are repelling each other, thinking of them as the magnets. But once they are interacting with each other, they naturally configure, so to speak, their spins in order to reduce the amount of energy of the whole system. And eventually, we will have a low energy state where all the spins are configured. And the energy reaches the lowest point. Sorry. And what's fascinating about this process to me was that this happens naturally. And it's unlike any kind of digital devices or the programs that we have. We need to specify the sequence of programming, how those spins configure with each other in discrete time steps. And the so-called Ising machine is really centered around such a physical system where we have a natural bifurcation, so to speak, a process where each spin is going by themselves to like a binary phase in this case. And in order to map, the Ising machine is to solve problems by mapping the Ising Hamiltonian onto that physical system and supply the additional energy onto it. Then we can then, once it reaches a lower or stable energy state, we can take measurement of those delta or spins configuration mapping onto the variables of our problem. And that turned out to be the solution to our optimization problem. In fact, the Ising Hamiltonian has a nice duality also in NPR problem called the quadratic unconstrained binary optimization problem. Before I move on to the first type of Ising machine questions. So the first type of Ising machines this paper introduces is called oscillator-based Ising machines. And what that is that we are using the phases of those oscillators to represent the spins that's in the Ising computational model. And in this case, they are resonating at the same frequency, in this case omega s, and in a binary phase states, either cat 0 or cat pi. And this is also called the Degenerate optical parametric. Sorry, it's a bit mouthful, but DOPO. This is a single DOPO spin device, and the property, we have two key properties enabling us to map them, to use them as the physical system. One is the frequency locking, which means that we have a pump, like a laser, providing additional energy to the system, and the spins are resonating at half of the frequency, and we have a phase lock. So we can see they are exactly shifted by a period or a pi, and mathematically speaking, they are one period out of phase with each other. The first spin with the second spin. Yes.
Just to point out here, there is another phase lock which is at pi by 2, but that's unstable.
Which phase lock?
So
Sorry.
in the phase locking,
Yeah.
so you mentioned two phase locks, 0 and pi. There's a third one which happens at pi by 2, but it's an unstable lock. So
Oh,
the system
okay.
can actually never sustain there. So that's a starting point.
Okay, I see. Thanks for finding it. Yeah. Yeah. So in this case, the paper focused on introducing one specific Ising machine. Such Ising machine is called the Coherent Ising Machine, or CIM. And what it does is just replace this physical system with a network of DOPOs. And we are programming CIP by coupling the oscillators in this network. And next, I will introduce an example from the paper that maps the max cut problem onto this CIM. In order to map this problem onto the CIM, in this toy example, we have 4 spins, right? And the max cut of this problem is in the middle, where we cut 4 edges instead of 3 or less. And in this case, we can introduce a so-called initial coupling. In this case, we have a J matrix, and the initial coupling is basically putting all of them out of phase. So in this case, we are putting them kind of at the highest energy level. And after a while, once this system stabilizes, if we get a solution like this, we can say half of the system, half of the spins is in a pi state, and half of them in another state, and this is the correct solution that we want. Otherwise, in any other configurations, we won't get the solution that we want. And it turns out, at least from the small scale experiments, you can achieve 100% solution, getting the 100% exact solution in this case. And the key question here, when I was thinking about this, is how we can put, how we can create this initial coupling, because it seemed to be super unnatural to me. And I was a bit baffled as to how we create this unnatural state where the system has a really high energy. And in the literature, I found an explanation. So basically, in this case, we have a pump and a network, and then a single oscillator. And the pump generates a pulse. And the pulse, in this case, we call it the dotted line circle place a cavity. So the pulse will move around in this cavity exactly in a pi in one period. And the length of it's a long oscillator, so you can bounce in one round, and the next pump will come on top of it exactly after that round. So they make the system long enough so that the traversal time exactly matches one period of that one. And this is a single DOPO. And then we can couple 4 DOPO together by introducing something called the delay lines. So in this case, we have one, instead of having one pulse in that cavity, we have 4 pulses in that cavity altogether. It's just that we are, as Professor just pointed out, we're timing the pulse when it back to that oscillator. We are putting the second pulse exactly on top of that one. So it's exactly synchronized, this process. And this will create separate periods and separate pulses in this case. The key idea is to introduce n-1 delay lines so that you can, once one pulse comes back, you can impose another one exactly on top of each other. If you have many interactions, then you basically, if you have a fully connected graph, then for each node you need to do this coupling for each and every connection it has. And I was wondering, so this is like a relatively toy example, and if you typically in digital solvers, in the digital solvers we have hundreds of variables, and how do we do that? And in fact, I think from the same group, they also developed something called simulated beam splitters. So instead of introducing like 100 delay lines, they are just using FPGAs to simulate what would have happened if we were to have this feedback loop. But yeah, I didn't really get into this one.
There's also like an electrical equivalent of it, where you create like an ASIC circuitry with RC with capacitors and resistors and inverters. And that is also like approximately simulates. There's like so many variants of the principle sort of thing.
Yeah, I guess that was what I was, yeah.
That was what?
That was what I was referring to.
Yeah, yeah.
Electric version.
But these systems are all good and fancy, but what's the problem here is that it doesn't change the problem landscape. So the NP-hard problems are still NP-hard. So you still have like the valleys and cracks you need to overcome. And so that's why this leads to the second type of solution, which is leveraging quantum approaches. And we could see potential tunneling used by those systems. But yes, so there are also works demonstrating that in the traditional, well, in CIM, you can also have quantum effects, but no one has actually proved how much contribution. Thanks for pointing it out. I think.
Sorry, go ahead.
Nice. I think that's a nice introduction to the quantum approaches. So in quantum annealing, we still have a similar but a bit more complicated mathematical formulation. In this case, we have so the qubits representing the spins instead of the oscillators, and in this case, we still have the classical Ising problem statement on the second part of the formulation. And here we are using the poly Z operator, the matrix applying onto every single qubit. So we have the little power Z there. But I think in the paper they mentioned it's commuting. This operator is commuting regardless of which direction you apply this operator. So it doesn't introduce the quantum effect, which is why we have the second term, the transverse field, where we have the poly X operator, which is non-commuting, and in this case, this operator pushes the whole problem statements to a superposition. And this introduces something called the delocalization effect. So, means that we still have the landscape, but it kind of, in the local statement, it bounces, it excites the whole system so that we can escape from the local minimum. And one interesting fact is about the A matrix and the B functions. So they are kind of knobs that we can tune. So at the start, we kind of want to explore the space by tuning up the energy applied to A, and then we gradually tune up the problem statement and tune down the A matrix, the energy applied to A part. That's the best intuition I can give from it. But the problem with the quantum annealing is that many times we need also dense connections. And in this case, yeah, I will introduce what this is later. But the hardware implementation restriction is that, for example, the D-Wave hardware is really limited to sparse connectivity, and which introduce the chimera graph like my sweater, but in this case we need to map one spin to multiple so-called unit cells, not exactly this unit cell, but the coupling among them. So this really introduces, in practice, a near quadratic overhead on top of the exponential complexity that we have. So I think one of the paper pointed out they had 2K qubits, but this number of spins were really limited to like under 50 because of this quadratic overhead. Yeah, thanks for introducing. This is fascinating because it reminds me of because of the hardware constraints, sometimes we need to introduce additional nodes. And then to make the problem still kind of correct, we need to introduce the penalty term, like the Lagrangian multiplier stuff, right? Yeah, this is fascinating. Yeah, now I get it why like the optimization landscape has been changed because of the. Yeah, actually there are also other approaches, memoristor, for example, and classical CMOS implementation in the paper. But yeah, I will skip this part. Yes. So for evaluation comparisons.
Can I make a comment?
Yes,
please.
please.
It's very interesting that they introduced everything in the paper except the simplest Ising machine, which is the easiest to understand, which is like a simple coupled oscillator Ising machine. So, no. So this is not the simplest Ising machine. The simplest coupled oscillator. So by this, sort of we are also in everything that we read in this paper, we are also assuming that these systems solve the Ising problem, right? Why? We haven't touched upon that part yet. We don't know. And for these machines, answering that why is very difficult. But there exists a very simple Ising machine for which answering that why is like extremely straightforward.
Yeah, quickly moving on to evaluation comparisons. So the evaluation matrix, the evaluation metrics introduced in the paper, well, they first discussed computational complexity, but they mentioned it's infeasible because most of the Ising machines are heuristic solvers, meaning that they don't provide any theoretical guarantees. And the additional benefits provided by them are constant, those constant terms, B and A in front of the base, or the constant in front of the exponent. So they introduced the empirical performance metrics. The first one is the probability of finding exact ground states in one shot. And but this doesn't introduce the concept, the concept notion of time, because one round could run forever. So they also use time to solution, penalizing. For example, in this case, we are having the exact solution being 0.0%. Sorry, the p success will be, the target will be 99%, and this will impose like an exponential penalty on that time. The evaluation workloads are two. First is the dense max cut instances they introduced, and the second is the SK problems. And this is the graph it represents that we introduced previously. So it's a slight modification or variant of the classical Hamiltonian, where we have not only possible connections, we could also take, the coupling could also take negative values. Instead of local interactions, we have full connectivity and so on. So in general, it's a much harder problem. And in this paper, they are not running, I'd like to point out, is that they are not running those experiments again. They are just collecting results from various original papers. And we will be looking at a bunch of different Ising machines. And the first, for example, we will be looking at the coherent Ising machines using FPGA and simulation, emulation. We'll also look at D-wave machines, those quantum annealers, and we will also have some simulated annealing, the classical approach on digital devices. And one thing I'd like to point out that those quantum solutions are using the chimera graph, so they're not all connected technically. So the first, they looked at the success probability. So in this case, on the x-axis, we have the number of instances. On the y-axis, we have the success probability we just talked about. And we have two evaluation scenarios. And the cases where we have asterisks, meaning that these are theoretical results instead of actual measurements. And as we can see first, we have the best scaling solutions coming out of the digital implementation, the simulated annealing, which scales exponentially with the number of instance size. And next, we can see that the CIMs are kind of comparable, but still having a slightly lower performance compared to the digital solutions. And what's interesting was that they pointed out the worst was the D-wave implementations, where they have a quadratic term at least on top of the instance size. And they mentioned that this was mainly because of the chimeograph, the coupling that we just talked about. Next, forgot this point. Next, we'll be comparing on the second matrix time to solution. Here, we're adding on to a bunch of other simulated annealing implemented on traditional digital devices and FPGAs and ASICs. So in this case, we set the target success probability to 99%. And the first we can see still the traditional digital implementation wins in this case, achieving the lowest time to solution. And this applies also to the max cut problem as well. We also have other digital implementations around the same ballpark. They are scaling around the logarithmic, the square root of the instance size with a fitting parameter c. Sorry. Remind me what TBM was. Yeah, TBM was the FPGA implementation of the bifurcate. And one thing I forgot to mention, the reason why the TBM really wins, they mentioned was probably because of the inherent parallelism, because at FPGA you have everything happen all at once, you have spatially distributed units, so the parallelism is massive there. Yeah, and also as Xian just pointed out, the parallelism here is defined by whether you can update all the spins at once. And as expected, the quantum solution performs still worse. It doesn't have the square root on top of the instance size. Before moving on to the class discussion, I will just quickly conclude. I will not state my opinion here because except that I don't think it's a really beginner-friendly tutorial paper that you should look at. I think the connectivity is really crucial, as pointed out by the authors. For Ising machines, they really dictate the performance of the Ising machines. And quantum annealing is limited by implementation, not necessarily by the computational model mechanism they have. And also, quantum mechanisms, how much they contribute is still a question. And the best solution are the classical digital methods that we currently have. But this is really new, right? Like the quantum annealing just being introduced recently and being tested physically now, only recently. So people are also looking to other potential solutions like quantum and classical solutions.